Hello, I'm Father Hugh Mackenzie. I'm a priest at Westminster Cathedral in London. I'm very pleased to be joined today by Dr. James Franklin, who's a professor of mathematics at New South Wales and has also written very interestingly about philosophy. Thanks for coming on, James.
Th-
Do you like to
Thanks for your
introduce yourself?
invitation. Great to be here from Australia.
Thank you. Today we're going to be discussing a debate that James has been having with William Lane Craig through various videos, and that's what the ticker says below, because William Lane Craig started it all. It's his fault by doing a very well animated video on the applicability of mathematics as a proof of God. And James then on the Analytic Christian channel responded to that. And then William Lane Craig on his own channel responded to James Franklin. So this is a response to William Lane Craig. He's also had a similar debate with Rationality Rules. That's Stephen Woodford. It's a prominent atheist, interesting channel. And he's also done last year quite a long video on the subject. And in 2021, a scholarly paper. We will refer to perhaps all of those things in our discussion here. William Lane Craig, many will know, is an evangelical apologist who has been a fantastic debater. Actually, I believe Christopher Hitchens said he's the one that all atheists were scared of. He's particularly good on his feat of turning any argument into a neat little syllogism. And in that regard, I think he's done a great service for theists and atheists alike in being involved in that sort of rise of good discussion, particularly during the pandemic and after the pandemic on YouTube and other platforms. So very grateful to him for that, and very interested indeed in all his work. So we're very pleased to be debating with him, even though we are really both, I think, disagreeing with him today. So in this, now William Lane Craig has various interesting arguments for the existence of God. The particular one we're focusing on is somewhat unique. It's from the Applicability of Mathematics, and it's based upon Eugene Wigner's famous 1960 paper, The Unreasonable Effectiveness of Mathematics in the Natural Sciences. The idea here is that the applicability of advanced mathematics to physics is very unexpected, from which Craig concludes that it points to a divine orderer or an intelligent creator who's made it in this way. James Franklin responded to one of Craig's presentations of that argument by arguing that mathematics is necessarily applicable and therefore is not surprising. And then Craig replied to him, and now the debate continues. The syllogism, succinct as ever, that Craig uses for this particular argument has this: A, if God did not exist, the applicability of mathematics would be a happy coincidence. B, the applicability of mathematics is not a happy coincidence. C, therefore, God exists. So James has, in effect, disagreed with both the premises. And the particular way in which this has happened leads us to present that disagreement in this way by highlighting 2 points of disagreement with regard to the first premise, and 2 points of mainly disagreement on the second premise. With regard to the first premises, the 2 points are to disagree with Craig, who affirms that mathematics and its objects, if it has them, are non-physical, causally inert and metaphysical. And then secondarily, to disagree with Craig's emphasis that such mathematics and mathematics in general is a priori to experience of the concrete realm, if you like, the objects of our sensations. And with regard to our disagreement on the second premise, this can be broken down into 2 points. The first one, where there's slight different of emphasis, I think, possibly between myself and James here, is to challenge the point of William Lane Craig that advanced mathematics is qualitatively different in the sense that there are non-physically realizable objects to advanced mathematics. And then the second point, where there's a clearer disagreement, I think, with Craig on our part, is that advanced mathematics is developed independently of its application to advanced physics. And therefore, we have this conclusion in a sentence picked out from his 2021 scholarly paper in the volume Contemporary Arguments in Natural Theology, where he succinctly says this: when we reflect that mathematical objects, even if they exist, are causally effete, it is surprising that such objects should be significantly affected in physics. So that's really his conclusion. So just before we go through those 4 points, I don't know whether, James, you want to sort of dive in right now and comment on that summary quote of William Lane Craig's argument for God from the Applicability of Mathematics.
Yeah, well summarised indeed. And if I could perhaps object to the very first thing that you have on screen there, the idea that mathematical objects are causally effete. Well, this Platonist view of mathematical objects is, of course, common, but I certainly would reject that. There is no Platonic world of causally effete abstract mathematical objects. There have been 2,000 years at least of objections to Platonism. For one thing, if there were those objects, if they were causally effete, there'd be no reason to think they exist. Whereas mathematics, as we know it, is very much involved in the physical world.
Lovely. Thank you. We shall now move on to just try and go through William Lane Craig's 4 points, and we're going to respond to each, and with some of them we'll use a video from his work. But this very first point, we've already given the quote, and he says that all over the place, and we have responded to the causally effete part. But just to say that William Lane Craig does assume or affirm that mathematics and the basic objects of mathematics are non-physical, and as we'll see very shortly, we're going to look at a video where he accuses, not in a very polite way, he accuses James of having the ridiculous position that mathematical objects are physical, that they are causally inert. He also tends to just say that therefore, I suppose, if they're non-physical, we can call them metaphysical at the same time. So, James, you've already responded to the causally inert. Do you want to say anything briefly before we look at some videos on the non-physical emphasis of...
Yes, I think we should just remember that we all know that mathematics tells you something directly about the physical world. And we know that, for example, 5-year-olds learn to recognise pairs and distinguish them from triples, and hence connect that to 2 and 3, without 5-year-olds apparently having some mysterious access to a Platonic realm. So let's keep in mind, as we go through the video, that everybody knows that mathematics tells you something directly about the physical world.
Excellent. Yeah, and as you point out in your book and your article on Aristotelian reason, we'll put links to all of these things, of course, below this video. Animals as well have a basic grasp of numbers.
Yes.
So that it does seem a bit strange. It's also to sort of say that obviously is taking on the whole sort of physicalist school, which may be building upon animals and indeed with some good, interesting physicalists, even things below animals, the way they relate to others. You know, there seems to be a relevance of quantity in the way even things below animals work. Similarly, the panpsychist school, which I think is an interesting school personally, but some people find that strange. But obviously, for them also it's physical. So there's a big discussion about that. Okay, so we shall move.
If I could interrupt a moment, you rightly use the word quantity, which is not talked about much in modern philosophy of mathematics, but that is what we Aristotelians concentrate on as what mathematics is about. It's quantities, whether discrete or continuous, measurements and so on. We should remember measurement. Yeah, measurement tells you something mathematical, but about the physical world. The ruler is laid there against the physical world.
just to add to that, I suppose numbers that have a universal character to them, that's a slightly technical term, but from the Greeks onwards, this idea of one applying to many, and numbers clearly applies to many. And in that sense, it's a universal. Yeah, it's a particular type of universal. But so what he says there would he would need to apply it to all universals, I think, which really would give him problems then. But okay, even bigger ones than the ones we're now going to show. So here we are, moving on to number 2, that he clearly says that it's an a priori discipline. So he says, mathematics is an a priori discipline, which is independent of the physical world. Mathematical concepts derive from the impulse in humans. And he also says it's unquestionably true that the concepts of elementary mathematics, and particularly elementary geometry, were formulated to describe entities. So there he seems to be moving slightly back in our direction. But as we're going to see in the next point, he is going to say, well, that's not true of advanced mathematics. So looking at that quote, some of the earlier stuff he's been saying about mathematics is really about advanced mathematics. And indeed, although that's not always clear, and your response to the presentation by William Lane Craig did sort of point that out, and then he came back and he said, I'm only talking about advanced mathematics. So we will be rapidly moving into that. But I just want to stop here just to look at a criticism of William Lane Craig directly of yourself, which is relevant to this point, so that you can actually reply to that point as well.
One of the very few philosophers of mathematics who takes mathematical objects to be concrete physical objects. And he defends this in his book, an Aristotelian realist philosophy of mathematics, which I read in connection with my study of divine aseity. It's a remarkable view. He thinks that mathematical objects are physical structures and entities in the physical world, that they are not abstract, they are actually physical. And so that's his Aristotelian philosophy of mathematics response that he didn't.
Just jumping a bit here where he developed this point a little bit.
Because on his view, you would have to say that these mathematical concepts are physically instantiated in the world. They are physical structures. And the problem with that is that, again, when you get to the higher mathematical concepts that Wigner is talking about, not all of those are capable of being instantiated in physical reality. When you get to things like complex numbers or imaginary numbers or infinite dimensional Hilbert space, which enables the formulation of quantum mechanics, then these cannot be physically realized. One of the best.
Okay, so James, do you want to first respond to his first point there, that you are saying that the objects of mathematics are physical objects or physical structures?
Yes, well, of course, I don't think that numbers are physical objects like stones. I think they're properties of physical objects like colours. So colours are not things exactly like stones, but they're properties of stones, and they have causal power. You know something is blue because the blue of the surface affects you. And mathematical properties are the same as that. They're repeatables like colours, but they're actually more relational. So let's take, by way of a concrete, and I don't mind the word concrete example, the ratio of your height to mine. That is something that's out there in the physical world, but of course it's not a thing itself. It's a relation between heights, and heights are properties of things. So I certainly think mathematical properties, ratios, symmetries, numbers, and so on, are physically instantiated, but that's not to say that they're physical objects. They're properties or properties of physical objects, or relations between properties of physical objects. Now, this is something that we Aristotelians keep saying, and that Platonists and nominalists keep failing to understand, because they think everything is a particular, whether abstract or concrete. But it isn't. There's properties of things as well, including physical properties.
Yeah, and of course, without properties, we can't really say anything about anything, really.
Well, yes,
Nothing. I don't think, frankly, there's any intelligibility to any object if it doesn't have a property, and you know, properties are what we how we access
that's right.
objective reality. At this
And
point, yeah,
and how
sorry.
how science accesses them too. I mean, if you take a physical law like Newton's law of gravity, it connects masses and force and quantities of forces. So they are exactly the kind of repeatables or universals that we're talking about here.
Yeah, lovely. Did you want to maybe at this point say something about this Königsberg diagram that we have here from your papers of the 7 bridges in that city with 2 islands, and there's a historical problem about
Yes,
whether one person can consecutively cross all 7 bridges.
yes. I think this is a terrific example of explaining the instantiation of mathematical necessities, mathematical properties, mathematical truths in the real or physical world. So this is a schematic diagram of the city of Königsberg in East Prussia in the 1730s when the mathematician Euler studied the problem. So there's top and bottom, there's banks of a river, and in the middle there are 2 islands. And there are 7 bridges connecting those land areas as shown. The citizens of Königsberg, when they were out on their weekend walks, asked whether you could walk over all the bridges just once without walking over one of them twice. Perhaps we should have a short pause while your viewers try to do that. So the problem again, find a route over all 7 bridges that doesn't go over one of them twice.
I suppose I should have some music at this point, but
Yeah, music would be good to calm people down because they're trying hard to work it out. Perhaps we should ask the viewers actually to pause for say 30 seconds and try and do it themselves. Let's say now that's done. The viewers, like the citizens, will after a while convince themselves that it can't be done. And Euler, the mathematician, proved this. And the basic idea of his proof is that if you go in and out of a land area, you must use up 2 of the bridges, the one in and the one out. And you can see that for each of the land areas, there's an odd number of bridges leaving it. Sometimes 5, sometimes 3. And it's that oddness everywhere that means a path over all the bridges just once can't be completed. Okay, well, that's a kind of mathematics called topology of networks, and invented really by Euler just to work on this problem, but a very big thing now, of course, in logistics, communications, networks, and so on. Well, that's a mathematical necessity, and it's got nothing to do with abstract objects in some other world. It's about the bridges and about the connections between the land areas. It's a provable mathematical necessity that can't be done, and it's about actual walking. So there we have the kind of thing that Aristotelian realists want you to see in mathematics: necessities, provable necessities, but implemented in the structures, the connections of the real world.
Brilliant, thank you. So we're still on this second point here, and I'd just maybe add to that when we do, and we're going to say more about this shortly, but when we do get to those advanced things like complex numbers and the extraordinary mathematics that is then discovered to apply to relativity theory, etc., that it's on this basis that those things emerge. Just to make that point at this stage, that we would have no mathematics of complex numbers without the basic laws of arithmetic, which indeed it's precisely because they apply to the square root of negative numbers that complex numbers have proved so significant.
Actually disambiguate the phrase a priori.
Yeah.
On one hand, it means that it's not findable in experience and that it's, so to speak, imagined purely in your mind. But on the other hand, it can mean that it's provable by necessity and that you don't need experience to prove it. And in the case of the Königsberg bridges, it's not a priori to experience in the sense that it is, you've made it up. It's in the bridges, those mathematical truths. On the other hand, Euler's proof of it is a priori in the sense that it's completely provable without having any empirical assumptions or anything. So perhaps I prefer to say it's a mathematical necessity. Mathematics is not an empirical science like ornithology or something where it's all, you have to take everything from observation. Nevertheless, you need the observation to get the concepts of quantity, networks, or whatever it is that are to be talked about by the a priori reasoning.
Yeah, I would just throw in the sort of difference, therefore, between the logical necessities, something that follows from concepts that we already have, and metaphysical necessity, which I don't think either of us are arguing for. At the end of the day, we're going to say that that which mathematics applies to, that is to say the objective world, is metaphysically contingent. But clearly logical necessity and inference and it follows from the meaning of identity, parts and wholes and all of that, which particularly in the light of modern science is profoundly important in understanding the physical, objective, contingent world.
That's right.
Yeah.
But having said that, the Aristotelian will insist that there are necessary connections between properties. To take a simple example, the betweenness relations between colours. So the way orange is and the way red and yellow are, it's absolutely necessary that orange is between red and yellow. So that is not a logical necessity, it's just how colours are and must be.
Yeah, although it follows from the way in which space and time and matter and energy have been configured. But so yeah, if you're going to make a color spectrum when you're a creator, then yeah, there are certain things, yeah, that will follow from that. So it's just to say that there are certain things which follow from the way in which you make something in which spiritual subjects will interact with each other. There will be some existential necessities, yeah, flowing from that. Okay, so we're just going to move on now to the third point here. Advanced mathematics is qualitatively different, and we'll just listen to William Lane Craig on this one again in his interview with a very good chairman from Reasonable Faith.
It's quite clear from what Wigner is talking about that he's not talking about these elementary concepts of arithmetic and geometry, like the circumference of a circle being equal to the diameter times pi. He's talking about the elegant and incredibly accurate sort of mathematics that plays a role in physics. Now, here's a quotation from Wigner's article showing this. He writes, "Whereas it is unquestionably true that the concepts of elementary mathematics and particularly elementary geometry were formulated to describe entities which are directly suggested by the actual world, the same does not seem to be true of the more advanced concepts. In particular, the concepts which play such an important role in physics. Most more advanced mathematical concepts, such as complex numbers, algebras, linear operators, and this list could be continued almost indefinitely, were so devised that they are apt subjects on which the mathematician can demonstrate his ingenuity and sense of formal beauty. So Wigner is not trying to explain the applicability of elementary arithmetic or elementary geometry. This could be a matter of logical necessity, as Franklin says. But he wants to know, why is it that the elegant equations of the mathematics of the laws of nature apply to the physical world?
Okay, so we have there his clear distinction between elementary mathematics and advanced mathematics. And he seems to be saying that advanced mathematics, which a key example is going to be complex numbers, is qualitatively different. Now, we've just in the previous point, I think we've highlighted that for us, it's all clearly rooted in a posteriori, non-a priori experience of the world. So should we now just look specifically at his examples? That is to
Yes.
say, infinity, complex numbers,
Well,
as apparently
sure.
examples of a qualitative difference, because the complex numbers, for instance, are very difficult to imagine. Square root of a negative number is actually not understandable in normal arithmetic concerning real numbers. And similarly, do infinities really exist?
Well, I would certainly deny the difference between advanced and elementary mathematics. The only difference is that it's harder, and the smarter the mathematicians are, the less they're worried about complex numbers or Hilbert spaces because they understand them. Of course, those who are not quite as smart get a little intimidated by them. But let's just take one of the simplest concepts, infinity. Well, we don't know whether that's implemented in physical reality or not, say the infinity of numbers, because we don't know whether the number of atoms in the universe is finite or not. There's no physical reason why it should be necessarily one or the other. And if there's more universe out there as you keep going out, well, there's an infinite number of atoms, and that infinity, the lowest infinity, is implemented, and maybe other ones are. I don't think there's any reason to think that any of the advanced mathematical concepts are in principle not realizable in physical reality. It just depends on how big physical reality is. So we live in a world apparently of 3 dimensions, but if we lived in a world of many more dimensions, perhaps infinitely many dimensions, well, we'd be able to construct all those very complex Hilbert spaces and other advanced things in wood. And I would put it by saying that infinities and all these other mathematical concepts thought up by very smart mathematicians could be realized, and usually they're thought up because to some extent they are realized. So Hilbert spaces, they're for quantum mechanics because quantum mechanics has that kind of structure.
Yeah, thank you. So yeah, no, so I'm with you that we don't know whether infinity is actually realizable, but were it to be shown, maybe somehow, I don't know, that it was not. Whilst there is something about infinity, maybe about the revealing something about the human mind going beyond limits, which it seems arguably animals don't seem to do because they're restricted within the ecological niche. It's not directly relevant to the argument of the implementability and therefore the applicability of mathematics to the concrete world. His other key example in a lot of his stuff, and indeed in Wigner's paper as well, is that of complex numbers, where it's been discovered that complex numbers make the proofs of some equations, particularly those involving the cube of the variable, which are called cubic equations, do help in at least in the efficiency of finding a solution to the cubic. And on top of that, we found that those type of solutions have applied very powerfully to quantum mechanics, for instance, which we wouldn't have foreseen. And it's that partly that lack of foreseeing the applicability of using complex numbers to solve equations, which William Lane Craig picks on, and he says, well, it's really just purely aesthetic reasons that we've chosen that we've gone down that road, and therefore this is going to be one of his proofs. So we've answered that similar point with regard to infinity. What about complex numbers?
Well, complex numbers, it's perfectly easy to realise them in the physical world, in physical motions of the plane. So the complex numbers have an additive and a multiplicative structure, so you can add and multiply them. Addition of a complex number can be represented as a translation in the plane, a kind of shift of the whole plane in some direction and through some distance. And multiplication by the square root of 1 can be represented by a anti-clockwise rotation through 90 degrees around the origin. And if you do those, you get exactly the structure of complex numbers, the whole structure with its addition and multiplication, physically realised in motions of the plane.
I hear you bringing in the concept, I think, of relationality again there. The negative dimension is relative to the positive dimension. And I think if you're offering the idea that in that sense of a relation, then complex numbers are physically realizable. Is that right?
Yes, that's right.
Yeah.
Perfectly.
Yeah.
Yes.
And in as much as you, James, are reflecting about the plane, a two-dimensional actual space in motion, relative areas are being highlighted, then this links with the 16th century discovery of complex numbers, which was doing something quite similar by representing multiplication as areas where the two sides of a rectangle are the two terms involved, and it'd be a square for x squared, etc., etc. Well, there's excellent videos on YouTube on how the complex number arithmetic was discovered as a sort of subset of solving quadratic equations. So we don't need to get into all that right now. Just to say that complex numbers in their discovery, in their use, are profoundly related to physical reality. Certainly, they seem to exhibit the ability of the human mind to go beyond what is physically realizable. I don't think that is important for us to reject, that to some extent there is non-realizable objects, because that is just humans going beyond what is easily applicable. Rather like my point on infinity, it doesn't create this other point within the second premise of William Lane Craig that we're about to highlight: radical independence of the mathematics to that to which it is applied. Complex numbers are, I think, possibly just placeholders within our calculation and our manipulation and our reflection upon relative areas. And we use the square root because that's part of normal solving of normal quadratic equations. And so you can get the square root of -1 because you can have a relative area, a negative area, compared to other areas that have been constructed through the calculation. So complex numbers are relative to and rooted in the nature of real numbers. And we will be moving on shortly, I think in our clip after next, to this point of independence of advanced mathematics from elementary mathematics that William Lane Craig has to and does affirm. And then towards the end of the video, we will just reflect about something I think we all agree on, that there's something about the human mind. I think it's this moving beyond immediate and direct applicability of what we're thinking about, which is interesting with regard to the sort of discussions that we are having.
Now, these are complex issues. The philosophy of this, it seems to me, is not automatic
No.
or simple, but to hitch our wagon whilst the philosophy of quantum mechanics and relativity is still in quite a young age, and there's lots of interesting stuff being done in these areas in the philosophy of complex numbers as well. To hitch our wagon to that by trying to say it's absolutely non-applicable, or well, what if it's absolutely proved that it is applicable, rather like infinity as well? Then we're all atheists, aren't we? Not that he doesn't have other arguments; he does have other arguments,
Yes,
but
of course.
this argument is going to collapse.
That's right. So certainly the development of physics has been more and more in the direction of exactly finding the mathematical structure of various parts of the physical world, which has turned out to be incredibly diverse and complex, but nevertheless it's actually mathematical, and the mathematics describes that structure.
And this has been a problem, particularly within the Christian tradition. And I was saying, well, there's something we don't explain, like say the relationship between the species of cat and species of dogs, and then evolution comes along and says, well, actually, we can explain that in the same way you've accepted explanations for simpler things. The simpler thing, what we thought was more complex, actually seems to be explained at the level of what was traditionally called secondary causation, or the physical interaction. Then again, that argument collapses. And I think I would argue, there's been something similar with the argument from first cause as well, as science has shown that the analysis of causation and act and potency and all of that is really an environmental thing. That's put pressure on that particular argument as well. So I think obviously we're not at all against using scientific concepts. In fact, we're sort of arguing that you have to in proofs, but you have to be a little bit careful with ones that are not yet determined. Okay, so there's another bit here relevant to this where William Lane Craig directly comes in on your argument that we've discussed a little bit earlier, but it's bringing in some of the points we've just been discussing on physical necessity.
What he's suggesting is utterly implausible. This is the alternative of physical necessity for explaining the fine-tuning of the universe, that maybe the laws of nature are necessary in their formulation. And that seems to me to be just utterly implausible. Cosmologists deal all the time with the possibility of universes operating according to different laws of nature. And I think it's really plausible to think the laws of nature are, in fact, contingent rather than necessary. So I think this is a rather desperate alternative for the detractor of design to take.
Okay, so whether you might want to reply to that idea there, James.
Yes, so I'm happy to agree that the laws of nature are most likely individually contingent, but their interconnections are not. Let me take a classic example. That Newton's law of gravitation is one law, and let's say it's contingent, and Kepler's laws of planetary motion are another law, and they're also contingent. But the former implies the latter, that if the law of gravitation is what it is, then free planets must revolve in ellipses. And that's a mathematical necessity. I hesitate to use the word logical necessity. It's how the law of gravity plays out mathematically when planets go around in obedience to that law.
Yeah, again, but you see, I don't personally see logic as some radically abstract realm either. So but I'm happy to use the word existential necessity. But I mean, I absolutely agree with the content of your point. There's certain necessity. Did you want to use your example of the circle as well? How the sort of necessity of the mathematics of the circle, and how that is highly elegant.
That's right. So Craig was praising Wigner for talking about advanced mathematics and its incredibly accurate predictions, but that's true in elementary mathematics as well. So take pi, the ratio of any circumference of a circle to its diameter. Well, it's been calculated to 100 trillion places now, the digits of pi, and which is a large number even by the standards of the US national debt. And it predicts what will happen if you choose more and more exactly circular parts of space. If you manage to produce a wooden part of space that's incredibly exactly circular, then those calculations will prove and give you a incredibly surprising prediction of what that ratio will be. And the more you get accurate measurement, the more you will be your predictions, the more digits your prediction will work out for. Now, that's exactly the same kind of thing as Wigner and Craig are talking about for advanced mathematics, but you see it exactly in elementary mathematics, which again shows us, I think, that those things are not really different, and that any surprise that is in there is due to the necessity of mathematics.
And indeed, here it is. Here is Wigner saying it's unquestionably true that the concepts of elementary mathematics, and particularly elementary geometry, like the circle, were formulated to describe entities which are directly suggested by the actual world.
So we'll move to our fourth disagreement with Craig's response to your initial response, which disagreement, like our previous one, mainly applies to his second premise. That is to say, the applicability of mathematics is not a happy coincidence. And this fourth disagreement of ours is with his statement, with his belief that advanced mathematics is developed independently of applicable advanced physics. And we have a clip here.
In his article, Wigner begins with very simple examples like Newton's second law of motion. And then he advances to quantum mechanics and finally to quantum electrodynamics. And it's an ascending hierarchy of independence of the physical world and more advanced mathematical ideas that just are not based in the empirical world.
So we're covering the similar ground, maybe from just from a slightly different angle, just filling out William Lane Craig's point there that for him absolutely there's this increasing dependence. Again, he hasn't really sort of got a clear line. He hasn't got a clear line when it switches from clear applicability of the elementary geometry to clearly not to the extent that it actually proves God. But
true, but it's called quantum electrodynamics because it is applicable to the physical world. It's invented because a mathematical structure was discovered in there that needs that kind of description. So it needs smarter people to do it than people who can just add up something. But it's not different. It's not different.
But he's again, just to remind ourselves, to be fair to him, he's saying that this mathematics was developed maybe partly because it's using perhaps complex mathematics and other equations beyond 3 dimensions, for instance, for Einstein's relativity, which would equations developed out of the aesthetic creative impulse.
Yes, but what does aesthetic mean, I wonder? I mean, I think our aesthetics are tuned on an understanding, an appreciation of the mathematical structure of the physical world. So a typical thing that especially physicists think is aesthetic is symmetry. But symmetry is exactly the kind of mathematical structure that is in the world, easily perceived in the world, for example, in rose windows in cathedrals. And the mathematical physicists have found that their aesthetic sense gives often a good guide to what mathematical structure will be found in somewhat hair-raising parts of the physical world.
So I would just also throw in again this phenomenon that humans, particularly even when we're doing experiments, but actually when we're walking down the street, in almost everything we do, we make predictions about the future that pavement will still be there when I take my next step. Now, it might not. Occasionally, some poor people, fall down a pothole. But we do have this ability to work out patterns from the past and then project them into the future given
Mhm.
particular conditions, and that an experiment really has just formalized that. So we're looking at possibles to a degree. So again, the human ability to look at possibles, I think we probably, or I certainly think, is an interesting thing to look at, which we may have time to do there. But uh, the idea that there are not possibles and potencies and potentialities within the objective world would seem to be crazy. And with respect, it's not too strong a word, but and when we're applying mathematics and in other fields of knowledge as well, we're often considering possibilities, which is fruitful to do, and through fantasy as well, we can do helpful, creative things. And it's not surprising, as what you've just said about beauty as well. It's not surprising because it's all based upon the concrete, actual dynamics, often of the past, that we have actually applied mathematics successfully to, and we're just looking at, often with great success, about how it might apply in the future.
Yes, that's right. When we are projecting into the future and imagining things, it would certainly help if we keep to mathematical possibilities, because if there's mathematical impossibilities, there's no point in trying to project or imagine them, because they're not going to happen.
Yes, indeed.
They can't.
Lovely. Great. Okay, so we move on to our final main point here, which is really perhaps fairly quick now, is just to say, well, I think we probably accept that if that third premise of his, that advanced mathematics is qualitatively different, were true, then in terms of its lack of applicability, lack of intrinsic applicability, even potentially, then we might accept that the argument might hold. So this fourth conclusion, I think, is a fairly natural one, and we can look at it in this quote we started with again here. That, as he says in his 2021 paper, when we reflect, which is in a book called Arguments in Natural Theology, book of papers in 2021. When we reflect that mathematical objects, even if they exist, are causally fate, it is surprising that such objects should be significantly effective in physics. Well, so if it particularly applies now, as we can see, to advanced mathematics and their whatever their objects are. So, do you accept the conclusion works if his premises are true? Yeah.
Well, they would be, yes, but there's nothing surprising about the applicability of advanced mathematics any more than of elementary mathematics, because it must apply. Mathematics is true in all possible worlds, and there isn't any need for an outside force like God or something to force reality to be mathematically as it is, because it must be. Of course, which physical laws are different. They appear to be individually contingent, so there must be some reason for it. But mathematical laws, no, they must be as they are. Like the ratio of the circumference to the diameter must be exactly pi for exact circles. Every mathematical applicability is the same, is like that in all parts.
Yeah, but just to come in on that point, if you're going to say that physical laws, that doesn't apply to, is that right? I mean, physical laws can be expressed by mathematical equations, can't they? On the whole,
yes, that's right.
If we believe in determinism, I think I would, then the physical laws are going to follow, aren't they, from the at least below man's freedom, just assuming we believe in freedom, but in outside of that, aren't we going to say that physical laws do have a certain logical or even existential necessity?
That's a very deep problem about what the necessity of any of physical laws are. They seem to be hard to get rid of, but I think that's a very separate question to anything to do with mathematics. So that if the law of gravity, Newton's law of gravity, is a contingent fact, nevertheless, the way it plays out, the way the consequences of it for planets or for things falling on the surface of the earth are then absolutely mathematically necessary, given that.
Given
that the original law of, and what the necessity of the, if any, of the original law is very hard to say. Gnomic necessity, as the philosophers sometimes call it, the necessity of laws, is a kind of necessity you have when you don't have necessity. Now, that's a very murky problem, but it's not a problem about mathematics.
Okay, we'll have to do another video on that one. Okay, so with that has completed our critique of William Lane Craig. Again, we have great respect for his work and thank him for his massive contribution to modern debate, which is one of the key sort of pioneers, I think, of making constructive debate, which has grown a lot in the last 10 years or so. So we would just wanted to say something positive, maybe just briefly, about the fact that we're not denying that there is something about the ability of human beings. I'm careful how I do this now, but to use mathematics in the way that we do, in the way that is, as it were, beyond limits, somewhat abstract, towards infinity, etc. It's not that the maths is not applicable, but that there is something about the and it's not that it's a priori, but it's just the fact that based upon our observation of the world, humans seem to have a sort of creative ability to go beyond. That's the way I put it, beyond limits. Would you put it in a similar way, or would you
something like that? I think this is something that Craig and I turned out to agree on, that there is something very mysterious about one aspect of human knowledge, the aspect of understanding, for example, understanding mathematical proof. If I could go back to the example of the Königsberg bridges, it's not just that it's necessity, that Euler's proof makes you understand why it must be so. Once you've understood that about using two of the bridges to come in and go out, you feel, yeah, now I understand why it's impossible for the citizens to walk over all the bridges once and once only. Now, animal knowledge doesn't seem to be anything like that. They don't get anything theoretically like that at all. But our knowledge of why things in mathematics and elsewhere must be absolutely so is really beyond the ability of animals, of AI, or anything like that to do. And it's, well, you have to say it's surprising in the way that Craig and Wigner was trying to tell us the applicability of mathematics was surprising. Well, it really is surprising. When I go in and go into a region in one bridge and out through another bridge, I've used up two of the bridges. There's only an odd number leaving each of the areas. So I'm not going, no matter what I do, there will be a mathematical obstacle to walking over the bridge, all the bridges once and once only. And you think, well, I understand not only that, it's not only that I am convinced that it must be so, I understand why it must be so. And that understanding is unique to humans and anything that's higher than humans. It's an aspect of consciousness, aspect of human consciousness. So AI, there's no even the beginning of a plan on how you could teach that to an artificial intelligence. The AIs are terrific at whatever they do, statistical analysis of human utterances and so forth, but they don't understand. There's nothing in there that could possibly understand. So this gives us some pause, I think, and if we said that humans are just, in fact, the same kind of thing as computers or cockroaches, well, we understand by looking inside ourselves that there is something, a step up, a step different, a qualitative difference. Very surprising.
So you don't think animals have maybe a certainly a very basic logic, but you're not talking about the intrinsic dynamic of inference here.
That's right. You can have
something beyond that. Are you?
That's right. You can have a kind. That's right.
the necessity of it, although
yeah, that's right. It's an understanding of necessity. So certainly cats can plot a path or something. They could and they could probably try to solve it. They probably get a problem like this and try to solve it if you put the rewards in the right place, but they can't understand the necessity of an answer. So I remember somebody pointing out that it's very surprising that we share 98% of our genes or whatever it is with chimpanzees, but the chimps themselves are not surprised by that, and they can't be, because they just don't get that whole theoretical perspective. They just can't understand the meaning of theory.
Yeah, got it. So getting to a sort of ability to, as it were, step back from the basic inference and look at its intrinsic nature is something
Yes,
important. Yeah.
I
Okay.
understand.
Yeah, I think we're on similar pages there, and just sort of saying that, well, this is something which is taking us outside of the deterministic, the purely existentially necessary. It's looking at human mind. It is showing something more and transcendently intelligent than the purely physical world. Is that right? Is
Yes,
that
that's right.
that's what we're looking at here? That
That's right.
in trying to be positive about this proof. Great. Now, here we do want to move on to how this approach to mathematics might help us with solving the problem of evil. I think you've
Yes, I'll
perhaps
just
talked
speak
some of
about
that
this
one. Yeah.
briefly. If it might be helpful if you got back the Königsberg Bridges
Oh yeah, right.
one again,
No problem at all.
because
This great software here enables me to do it. There we
okay,
are.
thanks.
Yeah.
Well, there's reasons why theists should be welcoming an understanding of how God is constrained by mathematical necessities. So, because the Königsberg bridges can't be solved, they can't be solved by God. It's something that is impossible. I mean, God could, of course, make different bridges or make walking different, but with the bridges and walking being as they are, even God can't make it possible to solve that problem. And that when we think about the necessity of laws of nature, I think we fail to grasp the mathematical interconnections between the physical world, and that how hard that makes it is even for an omnipotent God to do anything. All right, so people say to themselves, look, I don't like how God's made the world. I can imagine it better. For example, take a single stubbing of a toe. Let's have the world the same, but delete that. But there isn't any world that's the same as the present world, but with the single toe stubbing deleted, because that changes the impact of how physical laws are working in that around that particular case. And to understand how mathematically interconnected to understand the extraordinary level of mathematical necessary interconnections within the physical and, of course, mental worlds, is to understand that for an omnipotent and omniscient being, it looks good, but it's much harder than it looks to make things improve. And this is Leibniz's point. Leibniz was accused of saying that this is the best of all possible worlds and it looks pretty good, but he didn't mean that. He means that it's not only the best of all possible worlds, it's the worst of all possible worlds as well, because if you understood all the necessities that God has to deal with, not only physical ones, but in the interactions of people, then you would understand how hard it is, and you might be a little bit less eager to accuse God of not creating the best, doing the best he could.
Yeah, so sympathy for God there. Yeah, and I'm glad at the end there you're sort of linking it with human interconnection, because obviously part of the traditional answer to the problem of evil is to say, well, he wants to make us free in order to say yes to friendship with God, because the fullness of life and the fullness of love involves freedom. So he can't make a round square, as you're saying, and he can't make he can't force someone to be in heaven. And
that's right. That's just that's just one example, though. It's a good example in that it's obviously quite difficult to make people free and at the same time guarantee they don't do the wrong thing and badly affect other people. But that's just one example of the necessary interconnections. There's vast numbers of other ones of both physical necessity, of both physical and mental.
yeah,
Everything there. If God's got, you've got to think of God at the beginning trying to set up the world so that so that it's to some extent predictable, and so well, if you and that he's got to do this while keeping to mathematical necessities, because those necessities are absolute.
Yeah, and I think that ultimately that type of mathematical necessity is related to the relational dynamic that you and me are different people, and that is to me that's probably the sort of phenomenological foundation of mathematics, and I think Edmund Husserl was exploring that. And God, we believe he made angels who are pure spirits, like in our tradition, I think, who are purely in knowing and loving, knowing and willing. But he clearly wanted us to do this through a physical world of matter, energy, space, time. That is to say, a world in which our interconnections involve some of these necessities that we have been affirming, but the advantage of being in space-time, maybe compared to angels, is we can muck up and say sorry. But there are certain disadvantages, like the specific problem of evil that we have. So that I just want to. It's an interesting, the way you put it, and I think that's true. But I would think that it is intimately linked in with the fundamental desire of God to allow creatures to share His life as His children. So on that point, I think we can probably round off. And thank you very much for giving us so much of time and being very clear and on all of these issues. We hope it's enlightening for people, and that they freely and respectfully but engagingly put comments below, which we can still engage in, keep the discussion going. Thank you very much.
Many thanks. Very enjoyable.
See you again. Bye-bye.
Bye.